Hi, everybody. Thank you for joining me. My name is Mario Saldana. I'm from Roccor, and today I'll be talking about the work we've done on advanced thermal management devices for MIDS terminals. So Roccor's been around since around 2011, and they primarily used SBIR funds to develop technologies for deployable systems that made use of high-strength composites. So these high-strength composites use carbon fibers to deploy things like solar arrays, antennas, and scientific instruments on a spacecraft. They've also used SBIR funds to develop power technologies. So instead of just developing the mechanisms that would deploy a solar array, they would develop the whole solar array system. Also developing technologies for um, advanced power systems, so hybrid battery packs or battery packs with really high energy density. And then the area that I work in is developing thermal management products for high powered electronics. So the company primarily used SBIRs initially to develop this technology. Back in August 2020, when this presentation was put together, 75% of the revenue came from hardware delivery and 25% came from R&D. And those R&D funds were primarily SBIR based. Lots changed since August 2020. So in November of 2020, Roccor was acquired by a company known as Redwire that's been acquiring a bunch of other space companies, um, which is really exciting. You know, that's the goal when you start one of these small businesses, is to get it to the point where it becomes profitable and somebody would buy you out. Um, back in 2014, there was only 6 employees. At the time of this presentation, in August 2020, we were pushing 70, and now we're about 90 plus. Some of the successes that have come through this specific program was we were able to file a patent um, for this technology that we built for enhancing some of the um, thermal performance of these communications terminals. So the work for this specific program was in developing advanced thermal management for this high-powered communications terminal known as the MIDS jitters. They wanted us to identify and develop innovative heat transfer technologies um, that could be implemented to reduce the temperatures within the same form factor. Um, but now that you have higher performance in some of these modules, you need to be creative with the way you're going to remove heat or just lower the temperature of some of the electronics within these modules. The overall goal was to improve the heat transfer by at least 30%. Um, and not only that, you'd have to be able to operate over the um, environmental conditions that this system would be exposed to. So from -40 to 71 C, and then be able to meet the reliability standards. So be able to not only survive these environments, but be able to operate over a significant lifetime. So the MIDS Jitters terminal was undergoing several improvements. Taking that same form factor and in a couple of these slots that are available, um, giving it more capabilities. With these additional capabilities, though, you need to be able to maintain the electronics within acceptable temperatures. And these new capabilities usually involve higher performance, higher powered. So being able to mitigate some of the thermal issues, is a challenge. It was not only the Navy that was interested in some of this technology that we developed for this application. Um, NASA, the Missile Defense Agency, and IFRL have also expressed interest in being able to enhance um, some of the thermal performance of some of their systems for cooling spacecraft with increasing power densities, or also being able to cool some of these high-powered components within directed energy systems. So, think defensive lasers for shooting down drones or missiles, or using directed energy systems for interrupting comms and what have you. So the technology that we initially proposed to enhance some of the thermal performance within the MIDS jitters terminal was using these ultra thin heat pipes. Now, heat pipes are a heat transport device that utilizes water and an evaporation and condensation cycle to move heat. As we were going through looking at the design and strategizing on what would be an ideal thermal enhancement, we kept running into areas where our heat pipe technology just wasn't the right fit. So what we ended up developing was this product known as Roccor, which is a graphite-based thermal patch. And our goal with developing this patch was to be as minimally invasive, so making it so none of the vendors would need to really change any of their architecture, and this would be a solution that would be applied on, um, post design. Both technologies were really good at reducing temperatures. However, the ultra thin heat pipe was more invasive than the really thin patch that we were able to develop under this program. So during phase one of the program, we were primarily focused on investigating whether or not this heat pipe technology that we were developing was suitable for the MIDS jitters architecture. You know, this heat pipe that we developed had really high performance. We were able to move heat fluxes that were around 6 watts per centimeter squared, um, close, and having the overall package be only a millimeter thick. Um, this is in contrast to traditional heat pipes that normally start off round and then are smashed to interface with electronics. So if you want to cover a larger planar area, you need a bigger pipe. And if you need a bigger pipe, you can only get so thin. But because of the way our systems are built, we can get very thin. We can even get sub-millimeter. Um, 1 millimeter was kind of the ideal form factor that we wanted to hit. So we built up these systems, and again, they were primarily developed under this phase one SBIR. But then we took a second SBIR from NASA, and we actually got one of these heat pipes onto a technology demonstration mission to show that this system actually worked in its space environment. Um, we're really excited about the work that we were able to do with this specific technology, and we still see a bunch of uses for it um, on other applications. Unfortunately, it was not the correct solution for the MIDS jitters, as I mentioned earlier. So what we did we develop, and how did we get to that point? So the first step was to do a thorough analysis for the baseline architecture. So figure out, within this MIDS jitters terminal, looking at each of the cards, looking at where all the heat loads are generated, looking at where the heat's moving in the system, how the airflow moves through the heat exchangers on the top and bottom, identify, where are areas that we can add enhancements. And what we noticed is that on the exterior of some of these modules, there were these large thermal gradients. And we developed this sticker essentially that you could place around the exterior and essentially bridge some of the hot areas with some of the cold areas, but in a very thin package. So this thing just sticks on after the fact, doesn't interfere really with any of the other components, and it doesn't require a redesign. And we found that by adding these patches, we were able to significantly reduce the temperature, again, being minimally invasive, um, and something that could conform to complex areas. So you get this increase in thermal performance with just a minimal mass increase. So the next step in being able to make this technology successful, similar to some of our other programs where we were able to take SBIR funds, develop a technology, and commercialize it, was first is understand the customer. The Navy is the ultimate customer, but there's vendors that are actually working on developing this MIDS jitters terminal for the Navy. And this development is being undertaken by a joint venture between Viasat and what's known as DLS, or Digital Link Solutions, which is a combination of BAE, and Rockwell Collins. Both of these vendors work on different aspects of the MIDS jitters terminal. So one of the important portions of this work was to ensure that, for one, the vendors saw value in the solution and that we were able to actually demonstrate the feasibility. So where we got to at the end of phase two, which isn't captured here because it was recorded way back in August, um, is we were able to build one of these patches, deliver it to Viasat, have Viasat test it on an actual piece of hardware, and the most awesome thing was that our analysis matched up with what Viasat actually saw in the lab. You know, in order to take this further, we'd have to use a phase three program or some other type of mechanism for funding. One of the issues that we ran into when we were acquired by Redwire is we became a larger institution. And so we had options under this phase two program to keep this development going. However, having lost our small business status made it so we did not have access to those funds. So currently, we're at somewhat of a standstill, but the Navy expressed interest and they were very happy with what where we had gotten to in our development. And additionally, not only using research funds from the government, but exploring um, potential partnerships with other customers outside of the military. So working with commercial applications for things like telecom, server farms, directed energy systems, tactical satellite communication. So what do we do now? What are the next steps kind of moving forward? So the vision for this patch for this specific program was for us to supply the vendors with these thermal patches. They would initially integrate them into this MIDS jitters terminal, before they deliver to the Navy. But they would also provide these patches to the Navy for when uh, regular maintenance was carried out. Um, the airmen would go ahead and carry out whatever maintenance they had to carry out on the system, but also replace these patches. And for us to get to that point, our transition strategy was to get buy off from the vendors and the midge jitters office. And the way that would be done would be by taking these patches that have been shown to achieve the necessary thermal performance, but now you have to take them through the qualification exercises of, well, do these work in these different humid environments? Can they handle the temperature extremes? How do they do under vibe? And after being exposed to all of these environmental stressors, do they have the ability to have the necessary lifetime in between maintenance changes? We have to find an alternative path to get there outside of SBIR, and that's one thing that we're working on, is taking these promising pieces of thermal technology and running them through the rigor of these environmental tests to ensure that you know they do work not just for our Navy and our military customers, but for maybe some of these commercial applications. So at this point, I'd just like to thank you for listening. My contact information is here. I'd be glad to discuss or talk about any of the other thermal products and areas that we're working on, some of the battery technology um, that we're working on, specifically solid state battery technology. I appreciate you guys again taking the time, and have a good rest of your day.